cell panel, the ones we're going to be installing today, because this is a commercial installation and it's a bigger installation, we're going to be using 72 cell panels, which are actually going to be twice that with half-cut cells. And these are going to be Q cell panels that we're installing today. Anyway, they're basically the same width, just taller, and so while the 60 cell panels are about 66 by 40, the panels that we're going to be installing today are actually going to be closer to 80 inches tall by 40 inches wide. And then instead of weighing 40 pounds, they're going to weigh 50 pounds. So we're definitely going to want to work together when we're handing them up to the roof. We don't walk them up the ladder, we hand them up. You'll see pictures of that a little bit later in the slides, but you have at least 2 people on the ground passing them up to at least 2 people on the roof who are grabbing them. You want to use good communication and make sure that everyone's got a grip on it before you let go. So here's a PV array that's been fully installed on the roof. There's a very satisfied crew with the job well done. So how are these panels attached to the roof? Well, we've done a little cutout here where we're showing the rafters. The rafters are the strong point in a roof, and that's what we attach to, not just the plywood or anything else. We want to make sure that we identify where the rafters are and do our lag bolts and our solar feet attached directly to the strongest point in the roof.
And how do you find those?
That's a good question. It varies with different roofs. This one's going to be a little more challenging because it's soffit, but oftentimes you have rafter tails sticking out that give you a clue as to where the rafter continues all the way up. Some cases you just have to listen for them. You can't quite use a stud finder because there's too much material in there. But you can sometimes listen to it with a hammer and tap it. You can start to see where the more dense parts of the roof is. You always want to do a pilot hole first. I'll typically be doing the pilot holes because I have the experience in finding the rafters and knowing when I've hit the center of one. But it might take a couple of chances, and that's why the flashings are built wide enough that they can cover any holes that are to the left or to the right of your actual pilot that you know is good. But we're going to try to figure out where the nails are in the soffit and figure that's probably a good starting point to where to look for the rafters. So here's the system with the rails up, but the panel's not on yet. And what's the purpose of the rails? Well, that's going to be to separate sort of the rafter spacing from the panel spacing. The panels are about 40 inches wide, whereas the rafters, they're 24 inches apart. We usually use a foot at every other rafter, so every 48 inches. So because the 48 inches doesn't match the 40-inch spacing of the panels, you got to use something else. So attaching rails to the feet gives you this whole new surface that you can attach the panels to without having to worry about where the rafters are, other than when you put the feet in. So that's one of the feet right there. Here's a close-up of one. It's a little bit different actually than the one shown in this picture. This is kind of an L-foot style. The kind that we're going to be using is a concentric foot. It's from Iron Ridge. They call it the Flash Foot 2. But basically it's got the lag bolt going right through the middle there, and then it has a cap that goes on the top and it acts as a foot that you can attach your rail to. So there'll be more pictures of that later down the line. Here's an example of someone on a house pointing out where the rafters are. He's using the measuring tape, he or she, I'm not sure, but he's using the measuring tape to kind of say, this is where I see the rafter. The person on the roof is making a mark with a piece of chalk and sort of identifying where the rafters are so that whoever is doing the pilot holes can make sure they're drilling the right spot. So going back to how the power goes from the panels to the house, the PV modules, of course, generate DC power, and we got to get that DC power. Well, eventually it's going to get to an inverter, but we'll talk about that a little bit later. But first, how do we take the power and how do we route that wiring? So the PV modules themselves typically are, like a traditional array, are going to be connected in series. So you connect all the panels together. You remember the cells themselves are connected in series. Now you go from 30 volts per panel to connecting those in series and getting really high voltages. That's where things start to get dangerous. You want to listen to your project lead as to when you start connecting those panels together so that you get your timing right and don't shock the person who's working on the inverter. But yeah, just to kind of reiterate, voltage and power both add up when you connect in series. So your voltage in a 10-panel system is going to be 10 times, say, 35 volts, for example, would be 350 volts. And then if they're 290-watt panels, then you get 2.9 kilowatts out of a 10-panel system. And you can only put so many in series before you have to start a separate string, because you get to above 600 volts, then you actually exceed the capacity of the wire, and the insulation might not be rated for anything higher than 600 volts. Then you're going to have the electricity jumping the insulation and maybe going onto the rail and causing a short circuit and making big sparks. So you have to, in the design process, which is my job, I have to make sure that we design these systems properly and that we don't exceed the voltage range of the wires or the current rating for that matter. Today I should point out that we are using microinverters, so they're a little bit safer of the system, because we're going to have microinverters underneath each panel, and the voltage is never going to exceed the 240 volts AC, and then the DC side you're only going to have the voltage of an individual panel. We'll see in a little bit how the microinverters go together, but just kind of following along with the presentation, this is an example of a DC system with one circuit. So how do we get those wires down to where the inverter is going to be? Well, we use conduit. So that's a diagram of conduit going over the roof and then through the eave and then starting to go down the wall. This is what it looks like in real life. This is the drop wires from PG&E, and then this is the conduit that we put in. Notice there's a flashing there, special flashing just for the conduit to make sure that water's not leaking through the hole that we just drilled. So as long as we're looking at the PG&E lines, good time to point out, don't touch them. I think your wiring here is underground, right?
Yeah.
Don't have any overhead power lines.
No, yeah, to the street pole, it's all underground, right?
Yeah. So we're not going to have to worry about that on this particular installation, but in case any of you guys volunteer on future projects, just know that if you see that, that's not a post to lean on, that's not something to play around with. Granted, the wires should be insulated, but I've also seen that insulation broken down from being exposed to the sunlight too long, and really the only thing keeping those from shorting out to each other is just the gap of air between them. So anyway, don't touch them. Not only will this kill you, but it will hurt the whole time you're dying. That's what it says there. You can't make that up. So it's not a good way to go. Just give it appropriate spacing. Don't even get close to it so you can trip and fall into it. If anything, if the conduit needs to be that close, I should be the one doing that section of conduit. Here's an example of some conduit going down in the middle of the roof, kind of under the array, and going to an attic run. So that's the other option, is that you can run flex conduit through the attic. That won't be the case this time. Maybe a little bit.
We are going directly down to your panel.
Yeah, we're going to punch through directly to the service room. So not quite an attic, but sort of somewhere in between for this. But yeah, there's just different ways to do it. Whether if it's a long run that would have a lot of conduit running across the face of the house along the front of the roof, you might not want to see that. It might be something that's visually ugly, so you just run it in the attic instead. So it all just kind of varies from project to project, what's the best way to run the wires. So like I said, we have our DC on the roof, we have our AC going to the service panel. How do we get the DC to AC? Well, of course, we use the magic box that's called an inverter. I sometimes hear people call it a converter or other things, but it's an inverter. It inverts power from the straight DC river-like flow of current to the more wave-like sine wave back and forth current of AC. So we don't have to talk too much about how it works. It's just you have DC wires going in and you have AC wires coming out. So that's the inverter. We'll usually put it somewhere very close to the service panel. And then here's a picture of an inverter in real life. This is a SMA inverter. It actually has a a DC disconnect hanging from it. Nowadays, the inverters usually have it kind of more built in rather than hanging from the side. But either way, there's going to be some kind of off switch that disconnects the DC side of the circuit. And then sometime in certain jurisdictions, you'll also be required to have an AC disconnect box. We won't be needing that for this one. In this case, the circuit breaker itself will serve as the AC disconnect. But usually in some form or another, you have an inverter with a DC off switch and an AC off switch. And anytime you're servicing the panels or the inverter, you want to turn both of those off. Whether it's just turning off the breaker or whether you have a dedicated off switch. So I'm going to kind of throw this to the room, but what kind of wires should you have on the DC side? Let's say this is a single circuit. How many wires do you think are going to be running that DC conduit? Three? Okay. Any guesses to what those wires are?
Ground and negative and positive.
Exactly. That's right. You have, so if we're assuming one string, then you have one positive, one negative, and one ground. If you have two strings, then it's two positives, two negatives, and a ground. You can always share the ground wire because normally that shouldn't be used, and then it's only there for if there's a fault in one place or another. But the ground's basically going to connect to all the rails and all the metal parts that aren't supposed to be electrified. But just like the casing of the toaster, you want to have all your metal parts that aren't supposed to have current running through them directly connected to ground. So what about the AC wires? How many wires and what type of wires should be on the AC side of the circuit? Same thing? Not quite, because in AC you don't necessarily have a dedicated positive and negative because the positive and negative is constantly switching back and forth. What you do have is in AC you call it line 1 and line 2. So those are the red and black wires. You'll also have a neutral, which isn't really going to carry power in this case, but it might run the display of the inverter, and more importantly, it's just there as sort of a ground sensing that the inverter knows where ground is without actually using the ground wire for anything, because that's really, the ground is just going to be for grounding all the metal parts. But the neutral wire might have tiny amounts of current going on it, and it's just going to be a way that the inverter can detect that the sine waves from the two line wires are at an appropriate balance to each other. So here again is our flow diagram of the electricity with the inverter in place. So again, the power during the day is going to come from the panels, go through the inverter, get converted to AC, connect to a breaker in your AC panel, and then it's going to go some combination of back into your house with the excess going back to the grid. So what else does a solar inverter do besides simply convert DC power to AC power? Does anyone have any guesses as to what else an inverter is useful for?
Does it control the flow?
Yeah, it does control the flow. Like one thing it does is it can set the appropriate voltage for the panels, what we call maximum power point tracking. It turns out there's a perfect ideal balance of volts and amps that is going to create the maximum power out of the solar array. And if all the panels are getting the same amount of light, which is appropriate for a DC string inverter system, then you can pick that one voltage that works for all the panels in series. But basically, if you can have the highest possible voltage, which is in an open circuit. Remember, open means it's like the switch in the flashlight is open in the off position. When you do that, the voltage just builds up to a maximum point, but you have no flow, so you don't have any current. And wattage is volts times amps. It's the number, the amount of voltage times the amount of current. So if either of those values are zero, you end up with zero power. So in an open circuit, you don't have any power. Also, the other end of the spectrum would be a short circuit, where you have all current but no voltage because you don't have any load in place. You're not doing anything to slow the current down. In that case, if the current is allowed to flow as much as it wants, and then you lose any serious voltage between the two ends, and you have a short circuit where also the amount of power kind of paradoxically ends up being zero because it's you have 0 times the amount of current, so you really don't get any power out of that. But somewhere in between, those two values being 0, there's a point along the curve where you have the maximum area under the curve, where the volts times the amps is at its maximum, and that's called the maximum power point. And the inverter will constantly kind of test and look for what that maximum power point is, and make sure you're getting the most out of your solar panels for the given light conditions, because that maximum power point can change depending whether they're in shade or whether they're in full sunlight. The other thing the inverter does is safety checks, so it's going to check on the grid, make sure that, well, on the roof too, it's going to make sure that there's no ground or arc faults. As far as the grid, it's going to make sure that the grid is within the proper voltage range, that it's approximately 240 volts from line 1 to line 2. It's going to also